Hello, this is Professor Kuehn, and welcome back to Electricity, Magnetism, and Light. Today we begin our unit on Newton's Optics. This is Chapter 12 in a Student's Guide Through the Great Physics Texts. So what I'd like to do this week is because this reading is quite dense, I think what I'm going to do is read it to you, and as I'm reading it, I'll be commenting on it and making sketches to help clarify what Newton is talking about in his book, The Opticks. So here we go. I'm going to start with the introduction. Chronologically, our last chapter took us into the latter half of the 19th century with Helmholtz's famous statement of the conservation of energy. Now let us return, as it were, to the 17th century, that is the 1600s, to follow the concurrent development of the theory, or more precisely the competing theories, of light. We begin with the work of Isaac Newton, who set forth his corpuscular or particle theory of light in 1704 in his book called Opticks. Unlike his more famous mathematical principles of natural philosophy, sometimes called the Principia or the Principia, the Opticks was written in his native English. So you might recall, for those of you who've taken Physics 201 and have studied sections of Newton's Principia, that was written in Latin. You read an English translation of it. Opticks, what we're studying now, was written in English. It consists of 3 books in which the reader is presented with a litany of experimental observations touching on the nature of light. The first book from which the reading in this chapter is extracted begins with a succinct overview of the laws of optics pertaining to mirrors and to lenses. The reader who has studied Newton previously will perhaps notice that, like the first book of his famous Principia, the first book of his Optics proceeds deductively from carefully articulated definitions and axioms. It should be noted, however, that unlike in his Principia, the axioms presented in the Optics were generally agreed upon as having been empirically verified at the time of his writing. The following then should be seen as, and this is what Newton writes, as an introduction to readers of quick wit and good understanding not yet versed in optics. Okay, so let's start into it. Like I said, Newton begins with a set of definitions. So again, you might remember, if you've taken my Physics 201 class in the Principia, Newton started out with the definitions, for instance, definitions of quantity of matter and quantity of motion and impressed force and so on. After having provided these definitions, Newton then provided his axioms, which are then known as his laws of motion, the principle of inertia, F equals ma, and for every force there's an equal and opposite force. That's how he began in his Principia. So likewise here he's beginning with some definitions. So here we go. His first definition: by the rays of light I understand its least parts, and those as well successive in the same lines as contemporary in several lines. So you can see this is a bit dense. I'm going to read his explanation of this and then comment on it as I go. For it is manifest, that is, it is shown or known, that light consists of parts, both successive and contemporary, because in the same place you may stop that which comes one moment and let pass that which comes presently after. And in the same time you may stop it at any one place and let it pass in any other. For that part of light which is stopped cannot be the same with that which is let pass. The least light or part of light which may be stopped alone without the rest of the light, or propagated alone, or do not suffer anything alone, which the rest of the light doth not or suffers not, I call a ray of light. So what is he saying here? He's saying, imagine, well, think about it this way. Suppose that you were to have a window, and you were to punch a hole in that window. So let's suppose you have a window covered with a board, and you were to punch a hole in that board and allow a ray of light to fall into your room through this window. And it falls on the floor of your room, right? So you've probably seen something like this. So here is your board-covered window, or maybe it's covered with cardboard or something, boarded up like that. And he mentions that this light consists of parts both successive and contemporary. What does he mean by this? Well, he means that the part of light that is up here at the top takes some time to get to the bottom. So it's actually successive. It starts out here and it actually travels from point A up here to point B. That's what it means by successive. So in this region of light, there are successive parts, the part up here, and then later on the part down there. And also contemporary parts. What does he mean? He means things that are happening at the same time. So imagine if I consider a plane like this, all of the different regions of light are going through this plane at the same moment in time. They're contemporary, right? They're at the same time. And we know this because you can block parts of it and let other parts through. So if I were to take a board, let's say, and block half of this beam of light and let the other half through, well, what would happen is that this region over here would make it through. It can be kind of a funny drawing, but you're going to have a region over here that makes it through and lands on the floor. And the part on the right side would not make it through. Maybe I'll try to do that again. Let's suppose we have a beam of light. I'm going to draw a top view. You could take a board and block part of it like this, and then the other part of it would make it through and land on the floor. Okay, so this would be the blocked region on this side. On the right side would be the blocked region. On the left side would be the unblocked region. Okay, and he goes on to say, what does he mean by a ray of light? He means the smallest part that you can achieve by blocking the rest of it. So if you imagine moving this green board over to the left, more and more and more, until you have the thinnest conceivable sliver of light, that is what he means by a ray of light. Okay, it's kind of a limit of a broad region of light, a limit as you block more and more and more of it, so you're left with a single pencil of light or a single tiny little ray of light. Okay, that's what he means by his first definition, the ray of light. What about his second definition? So this had been definition 1. What about his second definition? What is he saying here? He's saying refrangibility of the rays of light is their disposition to be refracted or turned out of their way in passing out of one transparent body or medium into another. And a greater or less refrangibility of rays is their disposition to be turned more or less out of their way in like incidences on the same medium. So let me sketch something right away to give you a sense of what he's talking about. So the refrangibility of a ray of light, if you have, let's say, a glass block right here, and you take a ray of light and you have it impinge upon the surface, what's going to happen is it's going to bend like this. He's going to talk more specifically about how it bends shortly, but basically the bendability, how easily it's bent, is what he calls the refrangibility of that ray of light. It's a disposition to be refracted or turned out of their original direction. Originally it was going this way, but it got bent. Some beams of light are more refrangible or are refracted more than other rays of light. And we're going to see that it depends on the color of the light. And also it's going to depend on the two media, the media out of which the ray is coming and the medium into which the ray is going. So different junctions between different types of media are going to cause rays of light to suffer different amounts of refraction. Okay, so he says mathematicians usually consider the rays of light to be lines reaching from the luminous body, that means the glowing body, to the body illuminated, and the refraction of those rays to be bending or breaking of those lines in their passing out of one medium into another. So up here, if you had some object that was the source of light, this would be the source of light. It might be a light bulb or the sun or whatever, and then it's traveling like this in a straight line, and then it gets bent like this in going from one medium to another medium. Okay, and thus may rays and refractions be considered if light be propagated in an instant. But by an argument taken from the equations of the times of the eclipses of Jupiter's satellites, it seems that light is propagated in time, spending in its passage from the sun to us about 7 minutes of time, and therefore I have chosen to define rays and refractions in such general terms as may agree to light in both cases. So what is he saying here? He's saying that even if you consider light to travel instantaneously, that is, it wouldn't take any time to get, say, from the sun to the earth, even if you thought that, one could still study the refrangibility or the bendability of these rays. You would just draw these rays and consider it's all happening at the same time and not progressively in time. But he says we now know that rays of light do take time to travel from one place to the other. And in that case, when we draw a beam like this, it's bending going from one medium into another, you just think about this as successively going from the source to the thing that's being illuminated. By the way, he's mentioning here an experiment that we're going to read a bit about in the next chapter. Christian Huygens reports on some recent experiments by Olaf Romer, who had measured the time it takes a light to get from the sun to the earth. And he did that by carefully studying the eclipses of Jupiter's moons. So we'll come back to that a little bit later, but at this time he says it's known that light takes about 7 minutes to get from the sun to us. It's probably closer to 8 minutes according to modern measurements. Okay, what about his third definition, definition 3? So remember, he's so far talked about what he means by a ray of light, the fact that different rays of light get bent by different amounts, and that's their refrangibility. And now in definition 3, he's going to talk about the ability to bounce off of things, the reflexibility of rays. So he says the reflexibility of rays is their disposition or their tendency to be reflected or turned back into the same medium from any other medium upon whose surface they fall. And rays are more or less reflexible, which are turned back more or less easily. So if in the previous example we talked about a ray going from one medium into another, in this section we're talking about a ray of light that is bouncing off the surface of a medium back into the medium from which it came. So up here we had the ray going like this, here we're going like this. And so certain beams of light are going to easily bounce off a surface like a mirror, and other rays of light might actually penetrate into that material. And we're going to find that different colors and different wavelengths of light, when we get to the wave theory of light, have different tendencies to bounce off or to penetrate into a certain material. Okay, so that's what he means when he's speaking about reflexibility, is basically how easily it bounces off of a medium. Okay, let's go on to definition 4. Here's definition 4. So again, here's the definition of a ray of light in definition 1. Here is the refrangibility, or the bendability. Here is reflexibility. And here he's going to talk about angle of incidence. Okay, what do we mean by angle of incidence? He says the angle of incidence is that angle which the line described by the incident ray contains with the perpendicular to the reflecting or refracting surface at the point of incidence. So if, once again, I were to draw a surface that a light ray is incident upon or is striking, so I'll draw a line like this representing an incoming ray of light. If I were to draw a perpendicular line to that surface at the point of incidence of that ray, then this angle right here, this angle theta, would be the angle of incidence theta. Sometimes I'll write theta sub I, meaning the angle of incidence. Okay, and we haven't said here whether or not the beam is going to bounce off or whether it's going to go into the medium and bend, but in any case, the angle between the perpendicular to the trajectory of the incoming ray, that is what is meant by the angle of incidence. Okay. Definition 5. Let's go ahead and do this one before we end for the moment. So definition 5, I'll come up here and explain this. Definition 5, if back here he talked about the angle of incidence in definition 4, here he's going to talk about the angle of reflection. He uses an X because he uses an old English spelling. The angle of reflection and the angle of refraction. Okay, what does he mean? He says the angle of reflection or refraction is the angle which the line described by the reflected or the refracted ray containeth with the perpendicular to the reflecting or refracting surface at the point of incidence. So once again, let me draw our medium into which this beam is going to be traveling or off of which the beam is going to be bouncing. Here's the incoming ray of light. And once again, we draw a perpendicular like this. And then if we're considering a beam that's bouncing off like this, then the angle right here is what we mean by the angle of reflection. This is the angle of reflection. Okay? And if this goes into the medium instead of bouncing off, then we could also draw an angle here, theta, and that would be the angle of refraction, or the refraction angle. Okay. All right, so tell you what, I'm out of space, so why don't we stop there and we'll continue this next time.